Okay, let's start now. Good evening, everyone. I am Harshit Agrawal. Welcome to the 11th live session of mine for week 11 of the course Structural Dynamics CE07. So, in today's session, we will cover following things. First, we will just review what was covered in the last session, that was for week 10 of this course. Then, we will see what was taught in week 11, a brief overview just to brush up the content and get everyone on the same level. Then, followed by recap and overview, we will see series of two questions, each one different from the other based on the content covered in week 11 and assignment 11. I will first explain you the question and then step by step we will solve the question. So make sure you have a pen and a paper besides you so that you can solve along with me. So just like in the past sessions of mine, I will step by step guide you how to code in MATLAB and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else, just write the syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubts, can raise hand or write your query in the chat box. I will respond as soon as I will see. Okay, so let's start. So in the last live session that was for week 10 of the course structural dynamics, we talked about vibrations of continuous systems. Now, what are continuous systems? They are those systems where masses are distributed continuously throughout the length of the system and thus lumping of mass can't be done as we used to do in single degree of freedom system and multi degree of freedom systems. Apart from this, we also learned about seismometers. That is how theory of structural dynamics is used in making a device which can record seismic response activities. So, when we talked about continuous system, since the mass is uniformly distributed along the length, we saw example of a beam under shear action. Herein, we first dealt it with what's the governing equation for its motion, and then later on we derived dynamic equilibrium equation for it. Now, in this dynamic equilibrium equation, instead of normal mass, damping factor, stiffness coefficient, and force, we have generalized parameters. Now, what it means, we converted continuous system into a single degree of freedom system using generalized parameter so that it can be easily solved. Last session, we also saw one numerical and on how this conversion is done, and then how using basic single degree of freedom solution techniques that we have already learned, we can solve a continuous system and comment on its safety. And then we learned about seismometers. So a seismometer is a device that uses the theory of structural dynamics into practical application for recording responses of earthquake vibration. These are based on the basic concepts of undamped forced vibration in single degree of freedom system, and through a complex solution to the system, we saw how a seismograph can act as different response recording device. That is, when forcing frequency is smaller than natural frequency, a seismograph works as an acceleration response recording device, also known as accelerometer. On the other end, when the forcing frequency is larger than the natural frequency of the instrument, the seismograph acts as a displacement meter, and when there is resonating condition, it acts as a velocity meter. Now, last week, that is in week 11, we learned about dynamics of non structural elements. That are those elements which, though won't contribute to the load bearing function of a system, but upon earthquake vibration can become critical for damaging the surroundings. The content of week 11 was divided into different modules as in week 11 module 1 we read about basics of non-structural elements. What are they, how they can be in motion upon earthquake vibration, and how to check which kind of motion will prevail and thus offer suitable solution to it. And in the last module of the week, that is module 2, we then saw one numerical example wherein we commented on motion prediction of different non-structural elements at different floors of a multi-story building. So moving ahead, we'll just brush up all the formulae and relations we saw this week so that everyone can understand numerical and MATLAB part coming ahead properly. So just to brush up basic things of this course, the dynamic equilibrium equation is given as inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that the frame is rigid and deflection can happen only in horizontal direction and mass of supporting columns is negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. So this is something we have been reading since week 1 of this course. Now, from week 2 to week 6, all discussion were for single degree of freedom system. What are those? And many different techniques to solve dynamic equilibrium equation for a single degree of freedom system. But in reality, a structure is a complex system which can be seen more accurately as a multi degree of freedom system since it generally rises up to multiple floor and thus can't be concentrated as a single point. Thus, an actual complex structure is broken down into multi degree of freedom system in which number of floors is equal to number of degree of freedom, and thus this structure with concentrated mass of each floor and known stiffness of columns, assuming no lateral deformation or buckling, can be simplified into a spring block system as shown in the figure in the right. Therefore, we then saw about multi-degree of freedom system from week 7 to week 9, and we learned about eigenvectors and eigenvalues and modal shapes. And then later on, we learned about continuous system, the discussion over which we had already done. Now, in all these systems, we were only talking about load bearing elements. In simpler terms, those elements which can undergo internal deformation upon force action or which resist load. However, in reality, there are a lot of non structural elements also present in a building. What are these? These are those rigid elements which don't take any load but are a part of the building in different ways like aesthetics, utilities, and all. These elements are often neglected by the designers during design of a building, but later on can become severe source of damage to mankind upon earthquake vibration. Like even if the structure is stable under earthquake, these non-structure elements can become dangerous or others. So why they are critical? They are not the part of load resisting system of the building and are often neglected by the designer from design point of view. Now, earlier they used to contribute only 15 to 20% to the total building cost. So neglecting them was not that much critical. But now their contribution to the building can go up to 80 to 85%. So they become a critical part of the building. Now, what are these non-structure elements actually? So, they are broadly classified into three types: building facades, which includes glass facades and glass wallings on parameter, and second is building contents, which include furnitures and other accessories, and building services like electrical wires, water pipes, and all. So, these are some of the examples of non-structural elements. Now, how these non-structure elements can get affected? They can get affected either by force or by displacement or by birth. So, by force, elements which are stiff or massive and massive would be affected since they won't move much but they can get toppled or thus needed to be tied down. By displacement, non-structural elements which are light and flexible would be affected since they will easily deflect or move and thus needed to be bolted. And then there comes some elements which are both flexible and massive, which for which special care should be taken from falling debris and all. Now we know about what are non-structural elements and how they can be affected. But what kind of motions these non-structural element can occupy upon ground vibration? So if we take a simple rectangular block non-structural element upon action of an harmonic force or a normal force, anything, it can either slide, rock, or topple. Now, all three of them, sliding, rocking, and toppling, we can see in the diagrams how they look. Sliding is just movement, rocking is just deflection about a certain space that is occupied, and toppling is falling down. Like if the element is vertical, it will become horizontal. Now, what will happen when and what equations govern them, we will see now. So we know if the something is sliding, we need to tie it down. If something is sliding, we need to bolt it. If something is deflecting, we need to tie it. So we know the solutions of for all these, but now we need to know what will happen when and how to measure them. Okay, so first there is sliding. So when there is sliding, the baseline is in contact with the surface and there is only horizontal translation. And when sliding will happen, there are two conditions. When the push, which is acting on the element due to ground vibration, is more than the friction resistance, and when the restoring moment is more than the overturning moment. The restoring moment is generally due to the friction between ground and the non-structural element, and overturning moment is due to the external force that is acting on the element. Now, when there is rocking, the object just deflects about its base. So, in this non-structural element is not sliding, only angular movement of head and toe is present of at the base. Now, when it will happen when frictional resistance is more than the push, so that no sliding is happening. But overturning moment is more than the restoring moment, so that it can rotate. Okay, so what will happen? It will try to rotate, but it won't move, so it won't topple. It will just there and just deflect about its base. And finally, we have toppling, where element would just stay at its place only and would fall down. And in this, non-structural element loses its balance and ends up sideways on the surface. How it loses balance? Because both, you can see in the diagram, both the moment due to weight, that is the roundward orange arrow, and the moment due to the force, that is the horizontal orange arrow, both will be generating moment along the same direction, which will make the block to get toppled. And when toppling will happen, when it will happen, the friction resistance is more than the push because it is not sliding, and the overturning moment is more than the restoring moment. Okay. So here we also so in the lecture we also saw brief derivation for toppling condition, and now it is related to angular motion and other parameter. So all in all, the net governing conditions for each kind of motion are summarized in the following table. Here, AEQ is the acceleration due to earthquake ground motion. Omega is the frequency of the motion that is generated by the earthquake, and P is the frequency parameter. We will see later on how it is calculated. D is the width of the base and H is the height of the non-structure element, and mu is the coefficient of friction. So these are the relation. Based on these relations, we decide whether a certain motion will happen or not, and then we comment how to protect this element from that motion. So I hope the weak content is clear to everyone. So we'll proceed on with the questions now. Okay, so this is question one. A cupboard of 1 meter cross zero point 0.4 meter cross 1.5 meter, as shown in the figure 1, density is taken as 800 kg per meter cube, is placed along its length. A floor of the building starts to vibrate due to earthquake with an acceleration of 0.05 g at a frequency of 75 hertz. Check the safety of the cupboard in both directions for sliding, rocking, and toppling. Assume coefficient of friction to be 0.45. So I will wait for a couple of minutes for you guys to think how to solve the question, and then we'll proceed ahead. Okay, so we will see the solution now. So what was given in the question? A non-structural element, its dimension is given. We know the acceleration due to earthquake ground motion and at what frequency it is occurring, and the coefficient of friction between the non-structural element and the floor of the building. So first step is to always to determine the required parameters. Now in two directions the motion can occur because the dimensions of the base is 1 meter cross 0.4 meter. So along x direction the mass of the building will be same along both the directions. So mass is nothing but density into volume. So it is density is 800 kg per meter cube and volume is 1 into 1.5 into zero point 0.4. So it will come out to be 480 kg. Mass will come out to be 480 kg. Now, along x direction, the height of the non-structural element is 1.5 meter and the base is 1 meter. So, for determining the frequency parameter, we first need the r value. R value is nothing but the radius, which is given by under root of b square plus h square, the length of the diagonal. So, it will come out to be 1.803 meter, and the frequency parameter, as per the relation given in the slides, will come out to be 2.02 second inverse. And we know the frequency at which the base is vibrating, it is 75 hertz. So the omega will come out to be 2 pi f, which will be equal to 471 radian per second. So this is along x direction. Now along y direction the mass again will be the same, 480 kg. Height is the same, 1.5 meter, but the base width is now zero point 0.4 meter. So the r value will change. It will come out to be 1.552 meter, and the frequency parameter again need to be calculated, and it will come out to be 2.18 second inverse, and omega will be the same, 471 radian per seconds. So this is how we determine the required parameters along both direction. Now, first step is to check for safety against sliding. So there is a horizontal force acting due to ground vibration, and there is a backward force due to friction. Now, if the FEQ is greater than FFR, then sliding will occur. But at the same time, we need to also check whether it will topple or not. So the moment generated due to FEQ should not be more than the moment generated due to FFR. So FEQ into H by 2 must be less than FFR into D by 2. So we have simplified the relationships before also. So the two conditions are AEQ must be greater than mu G. If this happens, then sliding will occur. And at the same time, if AEQ is less than GB by H, then sliding will occur. Now substituting the values that we have in the question, the first condition is not satisfied, but the second condition is satisfied. Since one condition is satisfied and one is not satisfied, we can say sliding can happen along x direction. And similarly, along y direction, one condition is satisfied and second is not satisfied. So again, sliding can happen along y direction. We are not sure whether it will happen or not, but it can happen. Now, safety against rocking. So again, for rocking, there should be no sliding first, but there should be moment generated. So substituting the values in the relationships that we saw in the question. So since both conditions are not satisfied, so what will be the case? Rocking will not happen along x direction, and similarly along y direction, since both conditions are not satisfying, so rocking will not happen along y direction also. And finally, we have safety against toppling. So along x direction, we know the relationship that governs the toppling condition. So one relation is satisfied and one relation is not satisfied. So we can say toppling can happen along x direction. Similarly, along y direction, since one relation is getting satisfied and one is not getting satisfied, we can say toppling can happen along y direction. So this is how we comment on sliding, rocking, and toppling around x along for a non-structural element along its base. Okay. Now we know how to prevent them, so accordingly we can comment on the safety of the elements. So this was all about question 1. Now it's question 2. So what question 2 says, a structure to be analyzed is a three-story rigid steel frame shown in figure. The structure is subjected to El Centro's earthquake ground motion. The weights of the floors are indicated in the figure, and assume the width and the depth of the columns be 4 and 40 centimeter and 15 centimeter respectively, and the weight of the column to be 20 kilonewton per meter. Assume a non-structure element of 2 meter height and zero point 0.9 cross zero point 0.9 meter cross section is kept on each floors of the building. Determine whether the element is safe for any motion or not, and if not, which all motions can it possibly undergo into and their remedial measures. Assume the coefficient of friction to be zero point 0.2. So again, I will give you a couple of minutes to think about the question and the solutions ahead, and then we will discuss. हो गया आपका चेकिंग? इतना इजी पार्ट है तो भी इतने पूरा नहीं हुआ इतनी देर से। वो अभी कर रहे हैं क्या चेकिंग धीरज फिर? अरे यार, मैं सोच रहा था आज रूम में कॉपी ले जाता हूँ, सब खत्म करके वापस रिटर्न रख दूंगा सुबह। हाँ, तो आप तो इतनी जल्दी चले गए थे सर के पास। अच्छा, कुछ बोले सर उसका फिर? पेपर्स नहीं मिले थे? तो सर क्या बोले फिर? अटेंडेंस का नहीं पूछा था सर ने? ये फालतू में डरा रहे थे दोनों मुझे, कांड कर दिया इतना बड़ा, मतलब क्या फर्क पड़ता है, टोटल 48 की 48 है, फिर अटेंडेंस की क्या जरूरत? वो सर का मिड सेम वाला अटेंडेंस तो मेरे पास पड़ा है रूम में, सर ने लिया भी नहीं मुझसे। हाँ, कोई नहीं आया ना, सब आए। मेरा तो कल भी इन्विजिलेशन ड्यूटी। मैं उसको कम नंबर दूंगा, देखो उसको टॉपर से हटाता। मैं इस बार दे दूंगा यार इन लोगों को नंबर, वरना फिर क्रिप सेशन में फालतू में वापस से बढ़वाते हैं। नाइस जॉब। चलो हर्षित स्टार्ट। Okay, so let's see the solution now. So, in the question, we have been given a three-story rigid steel rigid frame. We know the dimensions of the floor and the columns and the weight of the floor columns. There is a non-structure element placed on each of the floor. So I will place a non-structure element at the base also. So we need to determine whether the element is safe for any motion or not. Now, how will we proceed for this question? So it is a complete solution from what we are seeing from week 6 till week 11. So what are the steps? First, we need to form the spectral response profile using Newmark's beta method for the L Centro's earthquake motion. Then we will obtain the mass and the stiffness matrices, and then we will calculate the eigenvalues and the eigenvector and obtain the periods of vibration. Now, from then we will calculate the participation factor and get the most critical mode of vibration, for which we need to check the safety of the non-structural element. So from the period of critical vibration, we will get the peak ground acceleration. Now this is horizontal ground acceleration, but the acceleration of each floor can change. So we will calculate peak horizontal acceleration of each floor using a standard relationship that I will discuss later on. And then once we obtain the the horizontal acceleration of each floor, we'll check for motion and safety of non-structural elements of each floor. So now I will be opening my MATLAB software in my laptop. You can see how to code now for now and implement it later on. We will go step by step, define everything properly and clearly. All the syntax that I will be using today are the same that we have used in the past sessions, but they are very important from the course point of view. So try to pay attention. I will clarify everything from time to time. But if you want to learn more, you can always visit MATLAB official webpage, and the more you will practice, the more command and clarity you will gain over these things. Okay, so let's see the code now. I will clear the screen first. Okay, so the first thing that we need to do, we need to import the data of El Centro's earthquake ground motion. So I have the file stored in my MATLAB folder. So we'll just copy both time and ground acceleration columns, and we'll import it in the terms of numeric matrix, and we'll click on the import selection. So once the file is imported, you can see in the workspace the database has a name and a value assigned to it. So the first step now will be to define the given values. So first we need to extract time data from the workspace. I guess someone joined the session and left. So El Centro data. So the first column is for time, and the second column is for ground acceleration. I will define it by AG. So we can see in the workspace in the right, both the mean data has been deconvoluted into two separate data sets. Now ground acceleration due to gravity G is 9.8. Delta T is nothing but difference between consecutive points in the time database. Mass will take as unity. Time period will be start from 0, and the length of the time data set we will define by tt, because it will be used later on in the loops. Damping coefficient is 0, and end point will define by 25. So the time till which we want to observe the time period till which we want to record the data. So for forming the response spectrum, what we need for each time period, we'll have a timestamp in which we'll record the responses. Then we'll get the maximum response for a particular time period. Then we'll change the time period, and for each time period we'll record the maximum response. And in this way, we'll form the response spectrum. We have seen this question before also, so I will just move on fast now. So first is the estimation part. In this, we'll start the first loop that will be for time period change. So it will be nothing but round of nt upon dt. So omega g comma 1 will be given by 2 pi t, 2 pi divided by tj. A will be omega square times m, so omega j square times m. And C, though damping is not present right now, but we will still define so that later on, if you want to replicate the code again, you have the base structure prepared. Okay, now we'll use linear acceleration method for calculating response. That is nothing but Newmark's beta method. So in this, first we need to define the basic parameters. So gamma is taken as 1 by 2, beta is taken as 1 by 6 for Newmark's method. Initial conditions, let's say initially velocity, acceleration and displacement all are 0. So u of 1 is equal to 0, v of 1 is equal to 0, and a of 1 is equal to 0. Now we need to define certain parameters that we require for Newmark's beta method. So it is k bar, a and b. So the relations for them we have seen earlier also, which I will just write the code for them. So k bar is given by k plus gamma c upon beta delta t plus m upon beta delta t square. So k plus gamma c upon beta delta t plus m upon beta delta t square. Then the second parameter that we require is A. So A is nothing but m upon beta delta t plus gamma c upon beta. So m upon beta delta t plus gamma c upon beta. And third parameter is B, that is m upon 2 beta plus delta t c times 0.5 gamma upon beta minus 1. So m upon 2 beta plus gamma c into 0.5 delta tc into 0.5 gamma upon beta minus 1. So the initial inputs will be u naught, v naught and a naught. So it will be the initial conditions that we have as of now. U naught, v naught, a naught. Now we have defined all the basic parameters that we require for Newmark's beta method. So the next step is to loop over each time stem so that we can record responses after certain time intervals, and then we can calculate the maximum response for each time period. So loop over each time step. So second loop will be for I is equal to 1 to pt minus 1. df will be given by minus g times the change in horizontal force that is acting. So it is nothing but agi plus 1 minus agi. Now we'll use the Newmark's functions that we have created. So that function we have defined earlier also. So I will just quickly guide you the function. So we have the input parameters will be t, a, b, dt, df, k bar, u naught, v naught, a naught, gamma and beta, and the output parameter will be t, u, v, a. So first we'll define df, then we'll calculate du, du dot and du double dot. So we know du dot and du double dot, so we can calculate the next displacement, velocity, acceleration, and will increment the time step. So this we have seen earlier also. So I will just directly call this function now. So output p comma u comma v comma a, and Newmark function, and the input will be p comma a comma b comma df dt a bar. We can see in the suggestion it is guiding us how what all parameters we need to input conditions gamma beta. So these are the parameters. Now after each cycle we will store the response. So we will store the response in a matrix, in different matrix for displacement, velocity and acceleration. So this will be for displacement, similarly for velocity, and then for acceleration. Now once we have stored the parameters after each Newmark function, we need to change the initial condition. So setting up initial values for next loop within a time period. So u naught will now become u, v naught will now become v, a naught will now become a, and t will be t only because in the Newmark function only we have incremented t. So this is how the inner loop will end. Now this loop will run regularly till the time p, the length of the time period that we have in the else intros function. Okay, so for each time period we will record around 1560 responses, and from those 1560 responses we'll get the maximum value for each time period, and then we'll change the time period, and for each time period we'll get the maximum value. So how we'll store these value? So the next thing is to estimation of maximum values at the given period. So u max will be nothing but max of absolute of ut1, v max will be nothing but max of absolute of vt1, and a max will be nothing but max of absolute of at1. So this is how we are getting the maximum values for a given period. Now again we need to estimate the spectral response now. So sd j comma 1, so we now will store these maximum value in a single matrix. So sd j comma 1 will be nothing but umax, for this is for the first time period. spv j comma 1 will be nothing but umax into omega. So this sdj into omega, this relationships we have seen earlier also. Omega j and spa j comma 1 will be nothing but sdj into omega square into g divided by g, and my time period will increase by my delta t. So delta t t j comma j plus 1 comma 1 will be nothing but t j comma 1 plus dt, and we'll end the second loop. So if both the loops are correct, there will be no error shown, and you can see in the workspace all the parameters and the final outcomes have been defined. So you can see in SD, SPA and SPV around 1 to 50 points have been defined. So for 1 to 50 different time periods, we have calculated the maximum response. Now we will just change the initial boundary conditions. Okay, so once we have defined everything, we'll just see the plot of the response now. So we'll define a figure. In this figure, we'll create subplot. So we'll create three plots in a single column and three rows. So for first row, subplot 3 comma 1 comma 1. So in this, we'll plot 3 comma SPA, the spectral acceleration response. Title will be spectral acceleration. X label time in seconds. Y label SPA. Similarly, subplot 3 comma 1 comma 2, so second row. So this will be for spectral velocity, and final plot will be for spectral displacement. We don't need spectral displacement and spectral velocity as of now, but still we will make the plot. Okay, so once we have defined everything, we can see the plot now. So this was our database, and this is how the plot will come out to be. So this is spectral acceleration versus time period. This is spectral velocity versus time period, and this is spectral displacement versus time period. Okay, so this is the first plot is what we will use later on. Now, the next step is to define the mass in the stiffness matrix and use the eigenvalue and eigenvector solutions to get the time period and then get the critical time period. So that for that we first need to define the mass in the stiffness matrices. So this is how we got the response of spectral. This is how we got spectral responses. Now determining system parameters for mass and stiffness. So these things we have done earlier also in week from week 8 to week 10. So it's nothing but the mass of the floor and half of the above column and half of the below column. So W1, W2 and W3 we can calculate, and then by dividing with the acceleration due to gravity we'll get the mass. And similarly, stiffness coefficient will get it is 12 EI by L cube, since there are two columns and two columns are in parallel, so it will be twice of 12 EI by L cube. So K1, K2, and K3 will get from that, and then we will define the mass matrix and the stiffness matrix like this, and then we'll solve the characteristic equation to get the solution for eigenvalue and eigenvectors. So we'll see in the MATLAB code how we get the solutions. These all things we have defined earlier also couple of times, so I have just moved on with them. So the next thing is to define the mass and the stiffness matrix. Define mass matrix. Mass matrix will be given by nothing but 2 4 4 times 0 0 0 comma 0 1 3 4 times 0 0 comma 0 0 6 5 3 times 0. So this is the mass matrix. Then stiffness matrix. So A is nothing but the values that we have calculated. You can see the matrix also, and now we'll solve for eigenvalues b and eigenvectors a. So a comma d will directly use the inbuilt MATLAB function for solving eigenvalue. So I k comma m. So what this will yield, so the eigenvalue d will be a diagonal matrix, and along the diagonal we'll have the square root of the elements of the entities along the diagonal will give us the omega, and eigenvector will get in A, so it will be a normal 3 cross 3 matrix since we have a three-story building. So you can see here D is nothing but a diagonal matrix which can be clearly seen, and A is nothing but a normal 3 cross 3 matrix. So how we'll read omega? So omegas comma k. So now this will help us to first will now the omegas can be arranged randomly, but which is the first mode of vibration, second mode of vibration, third mode of vibration? For that we need to sort. So we'll sort and we'll do the square root of diagonals of d. So what this will yield? So we can see the first mode of a vibration omega is 0.3883. For second mode of vibration omega is 2.1008, and for third mode of vibration omega is 3.8187. Now alternatively we can define calculate omegas like this also. So just omegas is nothing but square root of d. We can see how d came out to be, and we just get the square root, and then natural period be nothing but t is equal to 2 pi by omega. Okay, we wrote the wrong syntax. 2 pi next to omega. Okay, so this is the time period. Now we know the first mode of vibration will have the maximum mass participation, so this is our critical time period. Okay, but still if we want to check which is the as the maximum time period, so what you need to do from here, first you need to obtain the deformation matrix for each floor. So for that I will just move in the slides, and I won't wrote the code because we have that code from early lectures also. So this is how we calculated the natural frequencies. Now substituting the natural frequency one by one into the deformation equation, we can get first mode deformation for first mode of vibration, assuming deformation of one particular flow to be unity, then for second mode of vibration, and then for third mode of vibration. So for each mode of vibration we'll get the deformation profile. After this what can be done? From this we will get the we can calculate the participation factor for each mode of vibration. So it is nothing but the relationship for that we know. So we know the deformation profile for each floor, and we know the mass matrix. So basically we can calculate the participation factor of each floor, and after calculation you will see that the first mode of vibration participation factor will be maximum. So we are skipping that part, and we will directly move on with the part ahead, that is to estimate whether the non-structural element is safe or not for peak ground acceleration. So we know the time period for peak ground acceleration is 16.1794. So this is what we saw from the solution. So this is the critical time period that we have. Now for this time period we have the spectral acceleration response, so we'll calculate what is the spectral ground acceleration. So for the closest point to that point we get the SPA value to be 0.128343 g. So this is the peak ground acceleration. But now how this how peak floor acceleration can be calculated along the height of the structure. So for that there is a relationship that we can use. So for any floor ai is nothing but ci into a naught, where a naught is the peak ground acceleration and ci is floor acceleration amplification factor. Now how we can calculate this amplification factor? This amplification factor is nothing but dependent upon the height of the floor. So okay, so the relationship for that Ci is nothing but 1 plus 1 minus alpha times Hi by Hn, where Hi is the height of the floors that we are considering, Hn is the height of the uppermost floor of the building, and alpha is nothing but a period dependent factor. So depending on our critical period, alpha value will change. Okay. So in our case, since t is greater than 1, so alpha relationship will be 2.5 upon t to the power 0.75. The alpha will come out to be 0.31, and we know the floor height. So the height of the first floor is 20-meter, height of the second floor is 30-meter, and height of the third floor is 40-meter. So just calculating the acceleration amplification factor for each floor, we will get the acceleration amplification factor as 1.345, 1.5175, and 1.69. Once the acceleration amplification factor has been calculated, we know the peak acceleration of each floor now. So it is nothing but the acceleration amplification factor into peak acceleration of the ground floor. So the peak acceleration will come out to be 0.128 g, that is for the ground, then 0.172 g, 0.194 g, and 0.216 g. So these are the peak ground acceleration. Now we will talk about a non-structural element. So dimensions we know, mass will know. So we will first calculate the required entities that helps us to define whether the motion, which type of motions will it will undergo. So there are three critical entities: mu g, g into b by h, and ag into 1 plus 1 by 6 omega by p. Okay, so mu g, the coefficient of friction of between element and floor is given as zero point 0.2. So mu j will be zero point 0.2 g, and it will be constant for each floor. G into b by h, so b and h are constant since it is a square base, so we need to calculate the motion along one direction only, and it will prevail along the second direction. So g into b by h will come out to be 0.45 g, and ag into 1 by 6, ag into 1 plus 1 by 6 into omega by p. So we know omega is nothing but the ground acceleration, it is 16.22 radian per second, 0.3883 radian per second, and p we can calculate, we know the r value and we know the relationship. So upon substituting the values, we'll get the final entity as 1.03 g. So based on these values, we can check whether the non-structure element is safe for motion or not. So comparing the values from the relationships that we have discussed earlier also, so using these relationship between AEQ and mu g, AEQ and GB by H, and AEQ and AG into 1 plus 1 by 6 into omega by P. So comparing all these three relationships, we'll get the following result. So till floor 2, the element is safe for all three: sliding, rocking, and toppling. But at floor 3, the element is coming out to be not safe for sliding but safe for rocking and toppling. So, since the element is not safe for sliding at floor 3, what needs to be done? So, we need to, since the element will be affected by displacement, we need to bolt it down so that there is no motion in that element. So, this is how we'll protect the element from any causing any harm to the building or to the mankind inside. So this will be the solution for the question. So in this question we saw from the scratch how we'll first get the default response spectrum for a particular earthquake motion, then how we'll get the critical time period of motion, then from the critical time period how we'll get the peak ground acceleration and acceleration of each floor, and then from those values how we'll check the safety of a non-structural element. So this is the code layout for the question. So here you can see we did the coding till here, time period calculation. After that, you can change the top floor deformation to unity and calculate the deformation for each floor. So A31, A32, and A33 can be changed to unity, and other floor floors deformations can be calculated for each mode of vibration. Once we get that response deformation profile, we can calculate the mass participation factor. So the constant multiplication will be 1 comma 1 comma 1, since it's a three-story building, and we can calculate P1, P2, and P3. We can check individually what are the values, and summation of all three should be unity. So from that we will see that P1 will be the maximum. So that's why we chose the first time period as the critical one. So the critical time period for us came out to be 16.1794, and it was for omega value of 0.3883. And then we'll calculated the check the safety of the element. So this was all for today's lecture. If you have any doubts, I will be there in the meeting uh, till 8. Thank you.